CP of Arlington Memorial Bridge with 2 state anodes. Presentations by Brian Pailes of Vectors Technology.
Well, thank you very much. I'll be talking about the Arlington Memorial Bridge. So this is in Washington, D.C., constructed in the late 20s, open to traffic in the 30s, early 30s. So it connects between the Lincoln Memorial and the Arlington National Cemetery. It's on the National Registry for Historic Places. So reinforced concrete arch bridge, very beautiful bridge in a great part of D.C. So here you can see there's the Lincoln Memorial, and it comes over, and we're on the Arlington Memorial side. So 11 spans. It has actually a bascule center span, but that no longer actually works and doesn't open anymore. And so, and then it's a spandrel arch bridge, so it's clad with granite on the outside. So in 2018 to 2020, Kiewit and AECOM had the Design Build Award for rehabilitating this structure. And so Vector Corrosion Services, actually I work for Vector Corrosion Services, we were asked to support them on the evaluation, CP design, and QA/QC with the installation here. And I'll be talking about the restoration of this structure. The structure was going through a 75-year service life extension. And so as part of that, they did a complete deck replacement. And to the past people, it was actually, they used stainless steel for the deck. And the bascule span that I mentioned, that was completely replaced because no longer it needs to open. So they just had a steel span there. But the substructure, so the arches and the cross walls, all needed to be rehabilitated due to corrosion deterioration. And as you can see here, so as you can see here, you can see some corrosion damage on the cross walls. And so there are expansion joints at every pier, chlorides in this, de-icing salts in this area getting down into the expansion joints and causing corrosion deterioration. And so they needed, they wanted to install a cathodic protection system to at least get them, that would last at least 30 years to extend the service life of those elements. And so as, I'm not going to get into the chemistry, but as we all know, corrosion reinforcement, we're dealing with corrosion of the steel reinforcement. That's the anode. And in the electrochemical reaction, there's a cathode that balances out that reaction. And so when we start talking about cathodic protection, we want to make everything the cathode. So we want to make everything the cathode. There's no section loss, and so we don't have any deterioration. With anything, we're dealing with corrosion. So obviously there's the initiation phase. So we're dealing with where chlorides get into that concrete. They cause the activation of the corrosion. That corrosion expands, causes cracking and delamination of the concrete. First part of the project was really the investigation phase of the structure. So first was to identify, do sounding, visual inspection, to identify where the deterioration was. Where is physical damage today that they needed to chip out the concrete, replace that. But if they just fix that part of the structure, they're really not addressing the full service life, right? We need to get this structure 75 more years. So if we just repair what's physically damaged today, we're not really addressing future problems. And so the other thing that we needed to do was look at where is corrosion going to be active in the future so that we can prevent it from causing concrete deterioration. And so did things like chloride testing, concrete sampling, and corrosion potential surveys to look at where the risk for corrosion was high. And so comparing both where the damage was now and where the damage is moving, we can then provide a more effective durability and service life extension. And so with obviously the areas that are delaminated now, that's just concrete repair. We need to remove that concrete, clean that steel, put that concrete back. But the areas that will be corroding in the future, that's really what my talk is about. What are we going to do to mitigate that before it starts? We're not going to chip out that good concrete now to prevent it in the future. So what we're going to do is apply cathodic protection to stop that corrosion before it starts. Or maybe it has started, but it hasn't caused enough cracking and delamination of the concrete and to warrant a patch repair. And so really there's two forms of cathodic protection that generally people out there are familiar with. There's galvanic, and in the last presentation was kind of alluding to that with zinc. So where you take a sacrificial metal like zinc, aluminum, or magnesium, and in reinforced concrete, we only use zinc. You connect that to the steel, and it sacrificially corrodes and protects the steel. So that's galvanic cathodic protection. We're using dissimilar metals. In this case, it's typically zinc. And really all the metal is doing is giving up its electrons to protect the steel. So we can get electrons from lots of places. And so we can get electrons from a power source and push them onto the steel in the same way. So that's really impressed current is instead of using a dissimilar metal that has some finite number of electrons based on the amount of zinc we put in, well, we can put in an inert anode and put in a power source and deliver those electrons over a longer period of time. We can have more control over those electrons. And that's impressed current. But there's benefits and strengths to each system. Galvanic systems are typically easier to install, design. There's no, it's all embedded in the structure. There's no external electronics or anything. That's kind of the disadvantage of impressed current. You have external electronics and controls that you have to monitor. Galvanics are kind of a set and forget. So, there's ups and downs to using different systems. But in this project, we actually used what we call a two-stage anode, which actually uses both kind of together. A two-stage anode actually has both a galvanic and impressed phase together in a single anode. So it installs very similar to a galvanic system, but it has the power more like an impressed current system. So you get the advantages of both systems. So you have an integrated battery and a zinc galvanic anode. So the battery is your stage one. It produces a high current output to passivate the steel. And then the zinc maintains passivity. So to give you some background, to stop corrosion, you need a lot of energy. But to maintain passivity, so once we've stopped corrosion in a passive state, we need a little bit of energy to keep it there. I always think of the analogy of friction. I need a lot of energy to get the box moving at the beginning, but once I have that box moving, I need less energy to keep it moving. So the same thing in corrosion. So using a battery to discharge a lot of current early, you can passivate the steel very quickly, and then once that steel's passive, you can use a little amount of zinc to maintain that passivity. So it's a much more efficient design. You don't have external electronics anymore from an impressed current system, and you can install less anodes than you would normally with a purely galvanic system. Another thing we want to do on the project too is this is a rather large structure, right? We don't need to put cathodic protection on every square inch of this structure. Not every square inch is deteriorating. So really using the investigation that we identified at the beginning with the chlorides and the corrosion potential survey, we identify where there is active corrosion and install these in a targeted method to prevent corrosion in those areas. And so really, we're just installing the anodes in areas around patches to prevent any kind of ring anode halo effect issues. And then areas where there is active corrosion or a high risk for corrosion, we'll install it there to prevent and stop that. So it's a lot more cost savings than say, typically with an impressed current system, you might install it on the whole surface area, even areas that may not necessarily need it at that time. And so by doing a targeted approach where we're really just targeting the areas that are potentially risking for corrosion, we can save a lot of money for the owner and apply it just to where it needed. So here's the kind of, this is one span this is a plan view of one span. And you can see these are the cross walls here, and you can see the hatched areas on either end. So effectively at the end of every arch, there's expansion joints, and as we all would suspect, at the expansion joints, there's a lot of chlorides getting in. So the risk for corrosion in those areas was quite high. So we're targeting a lot of those areas. But outside of that expansion area, we're really just targeting some small localized areas where maybe there was cracks in the deck or leaky joints or something that got in there. So you can see this is a quite large bridge, but we're really only putting CP in a small portion of the whole structure. So clearly, if you're comparing this to, when they were first bidding this project, they were looking at CP over the whole structure. This is quite a reduction of that need, and obviously you don't need to put it everywhere if it's not corroding. And so you can see here, gentlemen on the right, there was some, effectively doing the corrosion potential survey, they can identify where those anodes need to go. And here they needed to put some along the bottom of this crosswall, but not in the upper parts, just where those orange dots are. So we're really being efficient with our cathodic protection. And so they installed those in the arch floor, the cross walls, and actually on the underside of the arch as well. The anodes went in based on the design as 22-inch spacing, and there were some zones that were just directly connected and installed, and then they also had a small number of areas that they monitored with monitoring stations to monitor performance as well. So around 10,000 of the total anodes were ultimately monitored in 62 different zones throughout the structure. But there were 10 times that amount of anodes installed. So really they're just monitoring a select few so that they get some performance data to ensure that the design and everything is working great, but you don't need to wire up everything as a monitored zone. And so here you can see the anodes going in on this is actually the abutment wall here on the right. You can see the grid, and so the abutments were had a high risk for corrosion, so there's a lot of anodes over the whole surface. And then you can see on the arch floor here, there's a little targeted area that they're doing right now here. So they're installing anodes and doing saw cuts to wire those anodes together, and so they'll grout those in. And then, this is what the cross floor actually looks like when it's done. You can kind of see there's a line of anodes right here. They get grouted in and cleaned up, but they get embedded right into the concrete. So all those wires are embedded in, so very durable system. And then here again, you see this is the abutment wall, so they have a concrete repair, so that's all physically damaged now, but there's the rest of the crosswall has a high risk for corrosion, so they're going to do the anodes in those other areas. So really targeting where they need to prevent corrosion. And the monitoring stations, we did, like I said, about 62, so we had little junction boxes throughout the structure so that somebody with a multimeter could go in and get the collected data from those zones. And they had different little types out there, but this is what they look like in the field. So an engraved panel with some sensors, reference electrodes that you can measure the potential of the steel, and then allow for to measure the current between the anode and the structure. So during installation, my team was out there doing QA/QC, verifying that the anodes were installed properly, and as the monitored zones came online, collecting daily measurements for performance to make sure the anodes are performing properly, and checking to make sure that everything is working correctly. And so for cathodic protection, we use NACE, National Association of Corrosion Engineer guides, to determine what the criteria for, are we meeting cathodic protection and things of that nature. So are the anodes working properly per these NACE standards? I'll show you a couple examples of some data here from those. So one is an arch floor and one's a cross wall. And so one zone has 121 anodes and the other has 193. And so, one was activated in November 19 and another was June 22, 2020. So as we're moving through the structure, they're activating different zones. And so this is kind of what the performance looks like, and I'll talk just a little bit about like what we're seeing here. But so there's reference electrodes embedded in the concrete. So what you're measuring is the potential of the steel and how that's being affected by the anodes. And so really when you first install the anodes, the steel is in a corroding state or near corroding state. So the potential is rather low. So negative 300, negative 350. Anyone who's kind of familiar with corrosion potentials, around 350 is where corrosion is 90% active. And then as the anodes start polarized, effectively electrochemically changing the environment around the steel, the potential of that steel will start to change, and you can see that the steel potential starts to move more electropositive, which is in the passive direction. And you can see over time how they change based on the temperature. And the blue line is temperature, by the way. So we always want to kind of calibrate because temperature will change that those values. But you can see here, we're in a kind of a corroding state, and then when the steel's finally passive, it jumps quite significantly up into a non-corroding state. And so that's kind of what the battery is intended to do, is put a lot of charge in to passivate that steel, and when it goes passive, we see this jump in the potential. And then you can see, anode current so effectively the anodes are pumping out current over time. And so this is anode current over time, but it's really highly related to temperature because that's resistance. So you can see as the temperature goes up, current goes up. As temperature goes down, current goes down. So as it gets colder, the risk for corrosion is lower. As it gets hotter, the risk for corrosion is higher. So the anodes work really with the temperature to combat the corrosion. Really what we want to see is that the steel is being properly polarized to protect. The anodes are properly polarizing the steel, and usually we want to see about 100 millivolts of polarization. And so over the course of the anode install, we're measuring how much polarization we're getting, and we're seeing that we're easily getting 100 millivolts, a slight drop. Maybe it got cold in September, and so we weren't getting enough, but 90 is very sufficient. So, we kind of see what charge, effectively the anodes are pushing electrons onto the steel, and so you can measure how much charge you're getting over time. Per the project specifications, the red dotted line was the criteria for reaching passivation. And so you can see based on the anodes that were installed in October, they reached that charge in about a year. And so here we have a zone that was installed in around May. And so, after a couple of months, it's still moving in the right direction. And in about a little over a year, we'll reach that dotted line. And so we'll track that over time as we were tracking that as the project was going. And so since we left site around November 2020, but we actually went back this March to collect a little bit of data and just to kind of see that the anodes are still performing correctly and everything's going well. And so we did some measurements and polarization testing on all of the zones. And you can, if you're not corrosion professional, but really what we're seeing is we want to see that the value that we measured at the time 0 versus this time that we see about 100 millivolts of shift. And we're seeing very good shift still in all of the steel. So that tells us that everything is still passive and working really well. So those anodes are actively changing the environment around the steel in those high risk areas and preventing corrosion activity. So in conclusion, target cathodic protection can be very efficient and cost effective. So we're just applying the CP where the risk for corrosion is high so that we can prevent and extend the service life of that structure. The two-stage anodes is very nice because we can get benefits of both a galvanic and an impressed current system in one. We don't have external electronics that could break down or be destroyed, but we also have a higher capacity in the anode, so we reach passivation much quicker than we would with a galvanic anode. This makes it very convenient for the owner because now he's got something that's durable that'll last the 70, the anodes will last easily 30, 35 years, and then he'll get a structure that will easily last well beyond that because it will be in a passive state and won't be corroding. And so he can go out and verify that in the 62 zones that are monitored. So periodic monitoring to kind of estimate maybe the anodes end up lasting longer. So with collecting data on every couple of years, he'll be able to project out those lines and see when the anodes will actually end up stopping. So with that, I'd like to thank everyone for your attention. If you have any questions, I'd be happy to answer. Or I'll be around in the exhibit hall and I'll answer any as well.
Thank you, Bob.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.